Hello, it's Brad here, and today I'm going to be talking about one of the more major updates that is coming, MAS version 4.0, and that is looking at the added work that we do for seismic considerations. And in particular, what I want to talk about today is the ductility verification. So what you see here is just a basic file that I have started here, where we have just a shear wall element. I put it the height at 4.4 meters. Nothing else has really been specified. And so if I go and look at my loads that I've applied, I have a lateral load here, 90 kilonewtons earthquake load applied to this element. And I've also got an axial load in addition to the self-weight that's already applied here of 100 kilonewtons. So since I have an earthquake load now, what you need to do is go to this new seismic tab that shows up here. And there are two different ways of handling this. So I'm going to assume that we don't fit into the simplified method. It's the new part of the seismic section of the building code for areas that have very small seismic considerations. And in particular, I've put in moderately ductile as my ductility. So this is a big change from what we had before, where basically if you wanted to take advantage of any of these higher levels of ductility to reduce your loads perhaps, you would have to do all the extra work by hand and sort of on your own outside of the software. But now this is built in, so I'm going to put moderately ductile. And since this shear wall element that we're looking at is not squat, we are going to require ductility verification. And so if you are looking at an element within a multi-story shear wall, perhaps that's not within the plastic hinge, then there's this option here that you can select. But since we do have a plastic hinge here, this entire element is going to be designed. So that's what all this red text is that you see here. So then going to the actual design, I've applied the loads already, so I can go ahead and design this element. And you'll see I come with the design here. You'll see that the rebar is spaced fairly closely together. And even though I have the partially grouted option selected, the wall is fully grouted. That is because it is specified by the CSA S304 Masonry Design Standard that for a plastic hinge of this type of wall, unless your axial load levels are below a certain threshold and your seismic hazard index is below 0.35, you don't really have the option of partially grouting that plastic hinge. That's why you see it's been fully grouted for you in this case. So all the results are here, but we have a new section of results, the seismic results. And so it's not really the sexiest change to this new version of the software, but there is a lot of substantial work that's being done sort of under the hood. And in particular, talking about this ductility verification now is something that's required. And it can be a fair bit of work to do by hand, in particular coming up with what the drift is at the top. So we have a new deflection tab looking at the different load cases. So if we look at the earthquake one, we have about 8.28 millimeters of drift or that you see that's happening up here. And so that is also taking into account what the ductility is, the importance factor. That's all being done as well. So looking back at that ductility verification, we can see some more results that show up there. I'll click on the interaction diagram quickly to show you it's floated fairly close to this envelope curve. That being said, if you want to look at any more specific values of where this is the inelastic rotational demand and the inelastic rotational capacity, you can click on the detailed results tab. And we have all of the different seismic checks that are being done. So you can see the seismic checks. This design in particular, because our axial load is below a certain threshold and we're in the plastic hinge, we can actually have a height to thickness of 30. But if I scroll down, you'll see I now have these strain values of delta F1 and our inelastic rotational capacity. There is a maximum that we can go up to that's shown here. And so this is the equation that we're looking at for coming up with that capacity, a function of our maximum strain and our neutral axis. And then our demand is a function of our loading. We have RD, RO, or that overstrength SFRS, force modification factor. And then we have this gamma W. It is an overstrength factor. And so we go ahead and we calculate that as well. So you can see in this case, comparing the nominal moment to the factored moment up to, or looking at either that or 1.3. And so you'll see we're just over that in this case. And so this is just things that MAS is doing for you. So what I want to highlight here is that now if you specify higher levels of ductility, then you will start to see maybe some errors related to this if you don't pass, or you'll just see it satisfied. And it's all just part of the moment and shear deflection or design when we're looking at these shear walls. So if I go and I increase the axial load, because if we look at the capacity, it is a function of the strain, but also the neutral axis depth is in the denominator. So by increasing C, which is what happens if we put more axial load on the wall, or we add more steel that needs to be coupled with in compression, then that basically makes it more difficult to pass this test because that reduces our capacity. So I'm going to go back to the load stage here, and I'm going to increase this from 100 to 400. And I'm just going to point out before they do that this design is actually working with just a 15 centimeter block, which is pretty difficult to do in a lot of cases, because especially if you have any additional stories resting above this design, that gets more difficult. And so if we go up to 400, we have more axial load. And what you'll see is when we go through and design it, we will get a different result. See, now it's using a 20 centimeter block. We have smaller bar spacings. And that is just because our C value is quite a bit larger now. And so the 15 centimeter unit, we would have had a larger C, and this design would have failed. So since we are still going through, I mean, we have a successful design. So if I look at my seismic, once again, these values will be different because it's a different cross section, different areas of steel, but we're still checking that. And that is how you can go through, and using MAS version 4.0, you can go ahead and perform a ductility verification. If you have any questions about any of these results, or you're not sure about the processes or the assumptions that are being done by the software in going through and performing these calculations, you can always contact the authorized MAS support, the Canada Masonry Design Center. We're available to answer questions, offer technical assistance, so feel free to get in touch if you need anything. Thank you.